In this video, we're going to talk about activation functions in regard to neural networks. Coming into this video, you're expected to have a basic understanding of how a neural network works, what a neuron is, and how neurons are interconnected. The architecture of a simple neural network can be seen here. This network has 3 neurons in the input layer, 4 neurons in the hidden layer, and 2 neurons in the output layer. Matlab's representation of the same neural network can be seen below that. The default hidden layer activation function for a pattern net is a hyperbolic tangent. We will discuss why that might be the default setting later on in this video. Activation functions can be found in both the hidden layers and the output layers of a neural network. An activation function defines the output of a neuron for a given set of inputs. It basically works by taking the input and scaling it to an upper and lower limit. An activation function determines how that input is scaled. There are many different types of activation functions, but I'll go through some of the most commonly used ones below. I will begin by looking at the most simple activation function possible. This would be a purely linear function. The problem is, this function does not alter the inputs in any way, and will never actually be used in a hidden layer for any real system. Later on in this video, I'll explain how it could be used in the output layer of a neural network. The only classification problems this activation function would work on for the hidden layer would be very simple problems that had a clear linear line that differentiated the two outputs, whether a circle was green or blue. The inputs to this problem range from -1 to 1 on both the x and y axis, as linear functions have no problems operating with any numbers. To implement this activation function in Matlab, purelin can be used. A purely linear activation function is not able to cope with any amount of complexity, which means it would only be used in hidden layers of networks for problems that obviously do not require machine learning. The next activation function I will look at is the sigmoid function. This function used to be used very commonly in neural networks, but not so much anymore. The operation of the function can be seen here. Any inputs to the function less than 0 would be set to 0, and any inputs greater than 1 would be set to 1. All inputs in between would be replaced as shown by this S shape here. The main flaw with this input is it's not great at differentiating negative inputs or inputs greater than 1. So for this example, I'll show a network that has a range from 0 to 1 on the x and y axis. As you can see here, a linear function would be unable to differentiate these two classes seen here, and a more complex activation function is required. To implement this activation function in Matlab, logsig can be used. This is how we might expect the function to help differentiate these two classes. The next activation function we will look at is the hyperbolic tangent, or tanh. This is the default activation function for the hidden layers of a pattern net in Matlab that we saw earlier. This function operates very similar to the sigmoid function, except it scales its values from -1 to +1 in the same S shape seen in the sigmoid function. So, the example for this will have inputs that range from -1 to +1. If you know your network will not contain any negative values, you should use the sigmoid function instead of the tanh function, as less information would be lost when the function scales the inputs down. Tansig is used to implement the hyperbolic tangent function in Matlab. This is how we might expect the function to help differentiate the two classes. The biggest problem with activation functions based on the sigmoid functions is a problem known as the vanishing gradient problem. This problem occurs primarily in networks with multiple hidden layers. When input to a neuron is scaled down by the sigmoid or tanh function, the values that are closer to the upper or lower limit can be hard to differentiate due to that S shape. Because the inputs are compressed when passed through the sigmoid function, data is lost in the process. This is why sigmoid-based activation functions are not used as commonly in neural networks anymore. This leads us to the most commonly used activation function nowadays, especially in deep learning. This function is known as the rectified linear unit, or ReLU. The ReLU function scales values from 0 to whatever the input to the neuron is, similar to how the purely linear function we saw at the beginning of this video. ReLU excels at more complicated problems that need multiple hidden layers, as ReLU does not compress any information. The example problem I've shown here is ideal for a ReLU function due to the complexity of the classification of the two outputs. The inputs to the network also contain no negative values, as ReLU essentially blocks out all negative inputs. Poslin is used to implement the ReLU function in Matlab. The expected output of a network with ReLU implemented can be seen here. Similar to the sigmoid function, ReLU has a very big flaw. This flaw is called the death of a neuron. Explained simply, this happens when a neuron gets stuck outputting a negative value, making the neuron inactive. As ReLU rejects negative values, the neuron will always output a 0. The leaky ReLU function can be used to counteract this problem, as this adds a small slope to account for negative inputs. There are other options that also resolve this issue, such as the ALU or max out functions. It is widely suggested to use ReLU function in deep learning. If you experience the dead neuron issue, you should try an alternative. The reason for this is ReLU is much simpler for a computer to process than the alternatives might be, and the alternatives may not always be relevant. The last thing I'll cover in this video is activation functions in the output layer of a network. This is a much simpler option, as in most cases there are two options. If you have a classification problem, as shown in examples above, you would use a softmax equation, which shows the probability of an output being correct. All the outputs would add up to 1, so if you had a neural network with two outputs, and one was 0.8, the other must be 0.2. On the other hand, if you were doing a regression problem, this is where you would use the pure linear activation function that we mentioned at the beginning of the video, as you want specific values outputted and not probabilities. Hopefully this video helped you have a greater understanding of what an activation function is and how it is used in neural networks.